Unit 6, pages 126 to 130, Nodes, Multi-Electron Atoms, and Electron Screening. Nodes. Orbitals have some regions in space where the probability of finding an electron is 0. The point on the curve below where the probability goes to 0 occurs when psi squared equals 0. This point where psi squared equals 0 is called a node. So here's a node when you're looking at a wave. It's the standing part of the wave. And so when you're looking at a graph, such as this, the node is going to occur where the probability equals 0, or is down here at its lowest. And so this would be the node, a point at the lowest possible location on the graph. Multi-electron atoms. In single electron atoms like hydrogen, helium plus, and lithium 2 plus, all of the orbitals in the same shell is equal to all orbitals with the same value of principal quantum number n have the same energy. We say that the orbitals with the same energy are energy degenerate. The figure below shows that in hydrogen the 3s, 3p, and 3d orbitals all have the same energy. In multi-electron atoms, such as helium, lithium, beryllium, etc., the energies of orbitals within the same shell have different energies. The energies are no longer degenerate. The figure below shows that the 3s, 3p, and 3d orbitals have different energies in a multi-electron atom. So if we look at this diagram, notice that when you have only one electron present in the atom, that all of these orbitals are of the same energy and they're all totally level. They're not occupied, which makes them degenerate sublevels. So there's only one electron. It's here in the 1s, which makes these degenerate and these degenerate sublevels. They have the same energy and they are not occupied. However, when you have more than one electron become present, then you have electrons here and adding them as you get higher and higher in atomic number. So notice that these are no longer level with one another. They have different energies. So they are no longer degenerate sublevels. And you'll notice that this is your lowest energy. Energy increases as you move up this diagram. So this has less energy than 2p, which has less energy than 3s, and then you go 3p, and you'll notice that we always go from 3p to 4s and then to 3d. Look at how similar the energies are between 4s and 3d, so it's quite close. But energy level 4 would still be considered the energy with the level with the higher energy. Electron screening. This plot shows the probability of finding an electron, psi squared, at various distances from the nucleus. So here would be the graph of a 1s electron, and notice that it has the greatest probability of being found at the nucleus, because it's energy level 1, which is closest to the nucleus. Then, if you have energy level 2, it's going to have a greater chance of being somewhat near the nucleus, but not as close as energy level 1. And then, if you have a 2p, then you have an upwards graph here. Full disclaimer, I am not perfect at explaining these graphs, so that's kind of the best that I can give you. Alright, why screening affects energy. So remember this diagram where we said that you've got a force pulling towards the protons and centrifugal force that keeps the electron from going towards the nucleus. Recall that in the Bohr atom, the positive and negative attraction of the electron for the nucleus was a major factor in determining the energy of the electron. In multi-electron atoms, screening can reduce the nuclear charge felt by the electron. This reduces the energy of that electron. So electron screening is why the 2s and 2p orbitals do not have the same energy in multi-electron atoms. An electron in the 1s or 2s orbital is much closer to the nucleus than a 2p electron. When electrons exist in the 1s orbital, a 2p electron does not feel as much of the nuclear charge. The 1s electron is screening or blocking the nucleus off to the 2p electron. As a result of the presence of the 1s electron, the 2p electron decreases in energy. The orbital moves upwards towards 0 energy. Notice that the screening effect is larger for the 2p electron than the 2s electron. The reason is the 2s orbital penetrates closer to the nucleus. The 1s electron cannot get in the way of the 2s electron as much as it can for the 2p electron. So the graphs of 1s and 2s are quite similar because they both have a similar orbit, but then you'll notice the 2p orbit can enjoy more screening from the 1s and the 2s orbits, and so that's why its graph looks so much different. The figure below, or the figure on page 130, compares the energies of the orbitals in hydrogen and lithium. there are three key points to recognize in this figure. As protons are added to the nucleus, all of the orbitals in the atom are lowered to more negative values because the proton-electron attraction has increased. So imagine that your nucleus is down here. Hydrogen has 1 proton in its nucleus. Lithium has 3 protons. So because of the added number of protons, you can see how much lower the 1s orbital is of lithium in energy than the 1s orbital of hydrogen. As protons are added to the nucleus, all orbitals move to a lower, more negative energy. Okay, so lowering the 1s orbital is an indication of an addition of protons in the nucleus. When electrons are added to the nucleus, the orbitals move to higher, less negative energies as a result of increased electron-electron repulsions. So adding more electrons is going to cause these levels to start spreading out because of the electron repulsions. As electrons are added to the atom, orbitals move to a higher, less negative energy as a result of electron screening. So they start spreading upward and outward. Orbitals with more electron screening have the most movement towards higher energies. The figure below shows that N=3 shell in lithium experiences the largest increase in energy. Electron screening also increases as you go from S to P to D. So the 3D orbital in lithium will have the highest energy and the 3s the lowest energy. So just looking at lithium, because of the electron screening experienced from the 1s electrons and the 2s electrons, this level is experiencing a lot of screening, and so it's going to move to a higher energy. However, it's got a stepladder here, meaning 3s has less energy than 3p, which has less energy than 3d. Or you could say of these, 3d has the most energy. So here's your note card. It's focused on electron screening, and what you want to consider is here you have 1 proton. Here we have 2 protons, but we have 1 electron in both scenarios. So it's a comparison of what happens when you add more protons to the energy levels. Notice here that the energy levels are all in their locations, and then when you add a proton, look at what happens to them. They all start moving closer to the nucleus because there is a stronger pull of the nuclear charge, and so all the levels have moved down toward the nucleus. Now, if you look here, we have 1 proton in both scenarios, but we have 1 versus 2 electrons. So when adding more electrons, look at what happens. Here you have 1 electron there, and then in the degenerate levels, they are all equal in energy and level with one another. But when you start adding electrons, the electron repulsion kicks in, and now you'll notice that the electrons start to spread upward, and notice the 2s and the 2p sublevels have no longer have equal energy. Now the 2p has a higher energy than the 2s does, and so they're no longer considered degenerate at that point. Here are the 4 graphs that you should be familiar with for 1s, 2s, 2p, and 3p.